In this guide, let's be precise about what OAuth 2 replaced. The authorization code flow is OAuth 2's primary grant type for user-facing applications. Here's what the actual HTTP looks like. And as of 2026, OAuth 2 is being consolidated into OAuth 2.1, an active IETF draft that bakes a decade of security best practices into a single specification. Identity Expert, powering you to be an expert in identity. Today we're unpacking OAuth 2, the authorization framework that powers nearly every API integration on the internet. Every time you click Connect to Spotify, allow this app to access your Google Drive, or sign in with GitHub, OAuth 2 is handling the permission negotiation behind the scenes. It's the foundation that every other protocol in this series, PKCE, OIDC, DPoP, PAR, FAPI, is built on top of. And yet the core idea is elegant. Instead of handing your password to a third-party app, you tell the service you already trust to give that app a limited, time-bound permission slip. A token, not your password. By the end of this video, you'll understand exactly how the authorization code flow works, why the 4 grant types exist, and what the real security risks are, the ones that every extension in OAuth's history was built to close. Before we look at any code, let's make delegated authorization concrete. Imagine you've hired a new assistant. You want them to pick up your dry cleaning, but you're not going to hand them your house keys. Instead, you call the dry cleaner and say, "I've authorized my assistant to pick up my order. Give them the items when they show up." The dry cleaner writes a claim ticket, a limited authorization, and hands it to your assistant. The assistant uses the ticket to pick up the dry cleaning. Your house keys were never involved. The assistant can only do the one thing you authorized. Nothing else in your life is exposed. That is OAuth 2. You are the resource owner. The dry cleaner is the authorization server. The claim ticket is the access token. Your assistant is the third-party application, and the dry cleaning your data lives at the resource server. The key insight is the separation. Your credentials never left you. The app never saw your password. It only ever held a scoped, time-limited permission slip that can be revoked independently of your account. Let's be precise about what OAuth 2 replaced. The credential-sharing anti-pattern worked like this. You want to give a calendar app access to your email contacts. The app asks for your email username and password. It logs in as you, reads your contacts, and stores your credentials for future use. 3 things go wrong immediately. First, scope. The calendar app has your full account access, not just contacts. It can read your email, delete messages, send on your behalf. You never agreed to that. Second, revocation. To remove the app's access, you change your password, but now every other app you authorized and every device you're logged into breaks too. It's all or nothing. Third, breach amplification. Your password is now in the app's database. If that app is breached, your credentials are exposed, and since most people reuse passwords, the blast radius extends to every other site. OAuth 2 solves all 3 by replacing credential sharing with delegated token issuance. The app gets a token. The token has a scope. The token can be revoked. Your password was never on the wire. The authorization code flow is OAuth 2's primary grant type for user-facing applications. It works in 6 moves. First, the client redirects the user's browser to the authorization server, including its client ID, the redirect URI, the scopes it needs, and a random state value for CSRF protection. Second, the authorization server shows a login and consent screen. The user authenticates and approves the requested scopes. Third, the server redirects back to the client's redirect URI with a short-lived authorization code and the state value. The client verifies the state matches. Fourth, the client makes a back-channel HTTP post to the token endpoint from the server, not the browser. It sends the authorization code, its redirect URI, and its client credentials. This is the crucial step. The code exchange happens server to server, off the browser's front channel. Fifth, the authorization server validates everything and responds with an access token, optional refresh token, and the granted scopes. Sixth, the client attaches the access token to API calls in the authorization header. The resource server validates the token and returns the requested resource. Your credentials were never sent to the client. The client only ever held a scoped, expiring token. Here's what the actual HTTP looks like. The authorization request is a get to the authorization endpoint. The client redirects the user's browser there. It carries response type equals code, the cliented, redirect URI, scope, and state. In modern deployments, PKC parameters code challenge and code challenge method S256 travel along. The authorization server redirects back with a code query parameter and the echoed state. The client verifies state matches. Then the client posts to the token endpoint. The body carries grant type equals authorization code, the redirect URI, and the client credentials via HTTP basic or assigned client assertion JWT. The token response is JSON. Access token, token type bearer, expires in, refresh token, and the granted scope. On error expired code, wrong redirect URI, invalid client, the server returns 400 with an error field like invalid grant and an error description. The resource request is the simplest part. Attach the access token as bearer in the authorization header. The resource server validates and responds with the protected resource. OAuth 2 has a well-documented threat model, and understanding it explains why every extension in this series was built. 3 attacks deserve close attention. First, authorization code interception. The authorization code travels through the browser's front channel in the redirect URI. A malicious app registered on the same custom URI scheme or a rogue browser extension can intercept it. This is exactly what PKCE RFC 7636 was built to solve, and why OAuth 2.1 makes PKCE mandatory for every client. Second, CSRF via missing or unvalidated state. If the client doesn't include a cryptographically random state value or doesn't verify the echoed state on callback, an attacker can craft a link that logs the victim into the attacker's account. The mitigation, always generate state, always verify it, bind it to the user's session. Third, redirect URI manipulation. If the authorization server allows wildcard URI matching, an attacker can register a subdomain or path traversal that captures the redirect. The fix, exact string matching on pre-registered redirect URIs, no wildcards. The broader theme, bearer tokens without sender constraining, are vulnerable to replay from logs, proxies, or memory dumps. PKCE, DPoP, and MTLS each close a different leg of that exposure, and every one of them starts here. As of 2026, OAuth 2 is being consolidated into OAuth 2.1, an active IETF draft that bakes a decade of security best practices into a single specification. The headline changes. PKCE is mandatory for every client, public and confidential, using the authorization code flow. The implicit grant is removed entirely. The resource owner password credentials grant is also removed. Redirect URIs require exact string matching, no wildcards. Refresh tokens for public clients must be sender constrained or rotated on every use with reuse detection. RFC 9700, the OAuth 2 security best current practice published in January 2025, is the authoritative hardening checklist. It formally requires PKCE, forbids the implicit flow, and mandates the issuer response parameter from RFC 9207 to defeat mix-up attacks. At the higher end of the security spectrum, FAPI 2 and the broader ecosystem are moving toward sender-constrained tokens as the default baseline, not an optional enhancement. Bearer tokens alone are no longer considered sufficient for high-assurance deployments. DPoP and MTLS are the mechanisms that close that gap. Next on identityexpert, PKCE, the specific mechanism that closes the authorization code interception vulnerability. Subscribe so you don't miss it. All primary sources cited in today's guide are listed on screen. You'll find direct links to the RFCs and specifications in the video description below. If this breakdown helped you understand the topic better, please subscribe to IdentyExpert. We publish a new protocol deep dive every week. Thanks for watching. If there's a specific identity standard, authentication flow, or security protocol you'd like us to cover next, drop it in the comments below. We build our content based on what the community asks for. Subscribe and hit the bell so you never miss an episode.